All right, welcome to Chapter 8 of Physical Chemistry, Chemical Equilibrium, Equilibria in Solution. So in this chapter, we examine some consequences of dynamic chemical equilibria. We concentrate on the equilibria that exists in solutions of acids, bases, and their salts and water, where rapid proton transfer between species ensures that equilibrium is maintained at all times. The link between Chapter 7, the previous chapter, and this discussion here is that provided the temperature is held constant, an equilibrium constant retains its value even though the individual activities may change. So, if one substance is added to a mixture at equilibrium, the other substances adjust their abundances to restore the value of K. So, starting with proton transfer equilibria. The reaction of acids and bases are central to chemistry and its applications, such as chemical analyses and syntheses. One particularly important application of proton transfer equilibrium is in living cells, for even small drifts in the equilibrium concentration of hydrogen ions can result in disease, cell damage, and death. Throughout this chapter, keep in mind that a free hydrogen ion, indicated by a proton, or H+, does not exist in water. It's always attached to a water molecule and exists as hydronium, H3O+. And this is something that, as we move into more advanced chemistry, is the most appropriate way to look at acid and water versus the way we may have introduced it in 100-level chemistry, where a proton was simply a proton. Now, with that caveat aside, if you indicate something is a proton in solution, you can also just assume on many levels that it's a hydronium. So you can use the two interchangeably, although hydronium is technically more correct. So, beginning with the Bronsted-Lowry theory of acids. According to the Bronsted-Lowry theory of acids and bases, an acid is a proton donor and a base is a proton acceptor. The proton, which is in this context means a hydrogen ion, is simply mobile and highly mobile, and acids and bases and water are always in equilibrium with their deprotonated and protonated counterparts and hydronium ions. Therefore, an acid, HA, such as hydrocyanic acid, HCN, immediately establishes the equilibrium shown below, where any generic acid, let me see here, HA, in aqueous solution, in the presence of water in liquid form, is in equilibrium with hydronium and the conjugate base, A-. And we can express this equilibrium with K of the concentration of hydronium times the concentration of the conjugated base, which are the products, over the concentration of the weak acid times the concentration of water. Now, some of you may be wondering right now, but we don't include water as concentration because it's liquid, not an aqueous solution, and we'll get to that in just a second. A base B, such as ammonia, immediately establishes an equilibrium as well. So let's take a look at that, where some generic base B in aqueous solution plus liquid water is in equilibrium with the conjugate acid, BH+, plus hydroxide. And we can also establish the equilibrium relationship for that with the K of the concentration of the species which are on the product side over the species of the reactant side. Now, in this equilibria, A- is our conjugate base of the acid, and BH+ is the conjugate acid of the base B. Even in the absence of acids and bases, proton transfer occurs between water molecules and the autoprotolysis equilibrium. So that's the natural tendency of water to also separate into its hydroxide and acid form. So this equation is shown as two waters in liquid form will always be in equilibrium with hydronium and hydroxide. And this isn't a highly favorable equilibrium, but it does exist. And so this is always present. Autoprotolysis is also called autoionization. As will be familiar from introductory chemistry, the hydronium ion concentration is commonly expressed in terms of pH, which is defined formally as pH equals the negative log of the concentration of hydronium in solution, where the logarithm is base 10. In elementary work, the hydronium ion activity is replaced by the numeric value of the molar concentration of hydronium, which is equivalent to setting activity coefficient gamma equal to 1 and writing that the concentration of hydronium equals, or the activity of hydronium equals concentration of hydronium over C, where C equals 1 mole per decimeter cubed. For example, if the molar concentration of hydronium is 2.0 millimoles per decimeter, where 1 millimolar equals 10 to the minus third moles, then pH would equal the negative log of 2 times 10 to the minus 3, which is, in this case, 2.7. If the molar concentration were 10 times less, at 0.2 millimole per decimeter, then pH would be 3.7. Notice that the higher the pH, the lower the concentration of hydronium ions in solution, and that a change in pH by 1 unit corresponds to a tenfold change in the molar concentration due to the log base 10 adjustment. However, it should never be forgotten that the replacement of activities by molar concentration is invariably hazardous because ions interact over long distances. The replacement is unreliable for all with the most dilute solutions, which, under biological conditions, is typically a decent assumption. Now, protonation and deprotonation. All the solutions we consider are so dilute that we can regard the water present as being nearly pure liquid, and therefore as having unit activity. When we set the activity of water to 1 for all solutions we consider, the resulting equilibrium constant is called the acidity constant, or Ka, of the acid. And under those circumstances, it falls out of the equation, which is standard for our consideration of acid-base equilibrium. So K sub A equals the activity of hydronium times the activity of the conjugate base over the activity of the weak acid. Now, we can adjust this to be the concentration of hydronium over C times the concentration of the conjugate base over C divided by the concentration of the weak acid over C in our equilibrium process. But this is a rather cumbersome expression, and it's normally just shown as equation 8.4b, which is, I think, in everybody's comfort zone for this particular class, where K sub A equals the concentration of hydronium times the concentration of our conjugate base over the concentration of our weak acid. Acidity constants are also called acid ionization constants, and less appropriately, because deprotonation is not a simple fragmentation into atoms, dissociation constant. Data are widely reported in terms of the negative common logarithm of this quantity, where pKa versus Ka is the negative log of Ka. So it's an analog for our pH scale. It follows that from equation 7.8, where delta G of reaction equals negative RT times natural log of K, that pKa is proportional to delta G reaction for the proton transfer reaction. More explicitly, pKa equals delta G divided by RT natural log 10, with natural log 10 equals 2.303. Therefore, manipulations of pKa and related quantities are actually manipulations of standard reaction Gibbs energies in disguise, which is just describing the tendency of the equilibrium reaction to move towards the side of deprotonation when all said and done. Now, the value of the acidity constant indicates the extent to which proton transfer occurs at equilibrium in aqueous solutions. The smaller the value of Ka, and therefore the larger the value of pKa, the lower is the concentration of the deprotonated molecules. In short, the higher the value of pKa, the weaker the acid. Most acids have Ka of less than 1 and usually much less than 1, with pKa greater than 0, indicating only a small extent of deprotonation in water. These acids are classified as weak acids. A few acids, most notably in aqueous solution, hydrochloric acid, hydrobromic acid, hydroiodic acid, nitric acid, sulfuric acid, and perchloric acid are classified as strong acids and are commonly regarded as being completely deprotonated or fully dissociated in aqueous solution. The corresponding expression for a base is called the basicity constant, or K sub B. So K sub B has an analogous sequence of relationships where the concentration of the conjugate acid of that base times the concentration of hydroxide over the concentration of the base is our basicity constant, K sub B, and we can express that as a log base 10, where pKb equals the negative log of Kb. A strong base is fully protonated in solution in the sense that K sub B is greater than 1. One example is the oxide ion O2-, which cannot survive in water but is immediately and fully converted into the conjugate acid hydroxide anion. A weak base is not fully protonated in water in the sense that K sub B is less than 1 and usually much less than 1. Ammonia and its organic derivatives, the amines, are all weak bases in water, and only a small proportion of their molecules exist in conjugate acid form. The autoprotolysis constant for water Kw is simply the concentration of hydroxide times the concentration of protons in solution from the dissociation of water into its two constituent components. And we can also refer to Kw as pKw with the log transform, pKw equaling negative log of Kw. So at 25 degrees Celsius, the only temperature which we really consider in this chapter, due to the complexity of not controlling that variable, Kw is 1.0 times 10 to the minus fourth, and pKw equals 14. As may be confirmed by multiplying the two constants together, the acidity constant of the conjugate acid, pH plus, of base B, the equilibrium constant for reaction BH plus hydroxide is in equilibrium with hydronium plus base, is related to the basicity constant of B. So what we can see here is that ultimately Kw is equal to Ka times Kb. So because of the autoprotolysis constant having a constant set 1.0 times 10 to the minus 14th, because we know that that's fixed, any acid-base equilibrium process taking place in water, if we know the Ka, we can automatically calculate Kb because we have Ka and Kw. If we have Kb, we have Kw, we can always calculate Ka. The implication of this relationship is that Ka increases as Kb decreases to maintain a product equal to the constant Kw. That is, the strength as the strength of a base decreases, the strength of its conjugate acid increases, and vice versa. On taking the negative common logarithm of both sides of equation 8a, we can obtain the following, which simplifies to the expression that pKa plus pKb equals pKw. So, and pKw, of course, equals 14 at 25 degrees Celsius. The great advantage of this relation is that pKb values of bases may be expressed as the pKa of their conjugate acids. So the strengths of all weak acids and bases may be listed in a single table, which is shown in table 8.1 off to the right over here. Another useful relation is obtained by taking the negative common logarithm of both sides of the definition of Kw, equation 8.5, which gives us the following. And this can simplify, of course, to a very common relationship where pH plus pOH equals pKw, or pOH equals the negative log of the concentration of hydroxide. This enormously important relation. It means the activities in elementary work, the molar concentrations of hydronium and hydroxides, are related by seesaw relationship. As one goes up, the other goes down to preserve the value of pKw. The extent of deprotonation of a weak acid in solution depends on the acidity constant and the formal concentration of the acid, F, its concentration as prepared. The fraction deprotonated, alpha, the fraction of acid molecules HA that have donated a proton, is as follows, where fraction deprotonated equals the equilibrium molar concentration of the conjugate base divided by the formal concentration of the acid. And that fraction is also expressed as the fraction deprotonated, alpha, equals the concentration of the conjugate base in equilibrium divided by the formal concentration of your acid, which is what it was prepared at. The extent to which a weak base, B, is protonated is reported in terms of the fraction protonated, and it has an analogous formal description. We can estimate the pH of a solution of weak acid or weak base and calculate either of these fractions by using the equilibrium table technique described in section 7.5. So, let's do a few examples. Example 1, assessing the extent of deprotonation of a weak acid. And the question is, estimate the pH and the fraction of, Okay, now I've got my throat cleared. Estimate the pH and the fraction of acetic acid molecules deprotonated in 0.15 molar solution of acetic acid in aqueous solution. Now, so the strategy for this is, the aim is to calculate the equilibrium composition of the solution. So to do so, we use technique illustrated in example 7.3, with X illustrating the change in molar concentration of hydronium ions required to reach equilibrium. We can ignore the tiny concentration of hydronium present in pure water. It's many orders of magnitude smaller than the ones created by this weak acid. Therefore, it falls out of the equations because of its insignificance in the effect. Once X has been found, calculate pH equals the negative log of concentration of X. Because we can anticipate that the extent of deprotonation is small, meaning the acid is weak, use the approximation that X is very small to simplify the equations, meaning we get to bypass the use of the quadratic equation. So we can draw this ice table up as indicated, where we have our different species with our acetic acid, our hydronium, and our conjugate base, acetate. And our initial concentration, as prepared, is 0.15 moles per liter acetic acid. And initially, before it gets the opportunity to dissociate, we have no acid dissociated and no conjugate base formed. Now, once it reaches equilibrium, the equilibrium concentrations aren't yet known. However, we do know that we have a 1-to-1-to-1 molar relationship or stoichiometric relationship in this reaction. So we know that the equilibrium concentration will change for the acetic acid by the quantity X. So it will go minus the quantity X moles per liter, and therefore the amount of hydronium formed and conjugate base formed will be plus X. We can therefore describe the equilibrium concentrations as, for acetic acid, 0.15 minus X. And for the conjugate base, acetate, and hydronium, each of them will just simply be X. The value X is found by simply inserting the equilibrium concentrations into the expression for K sub A. So K sub A equals the concentration of our hydronium times the concentration of acetate over the concentration of acetic acid. Therefore, that will be X squared over 0.15 minus X. We could rearrange this expression to a quadratic equation and simply solve. However, it's more instructive to make use of the smallness of X to replace minus 0.15 minus X by 0.15, because X is functionally so much smaller, its effectively 0 in terms of our significant figures we're working with. And because of this, you can simply solve as shown here and here. Now the following example, assessing the extent of protonation of a weak acid, or excuse me, of a weak base, in this case, quinoline. So the conjugate acid of the base quinoline has pKa equal to 4.88. Estimate the pH and the fraction of molecules protonated in a 0.010 moles per liter aqueous solution of quinoline. So in this particular question, the strategy would be the calculation of the pH of a solution of a base involves one more step than that for the pH of the solution of an acid. The first step is to calculate the concentration of hydroxide ions in solution by using the equilibrium table technique and to express it as pOH of the solution. The additional step is then to convert pOH into pH by using the water autoprotolysis equilibrium, equation 8.6, where pH equals pKw minus pOH, with pKw equaling 14.00 at 25 degrees Celsius. So in this particular case, we do everything very, very similarly. We set up an ice table, and also note that we first write pKb equals 14 minus 4.88 equals 9.12. So because the pKa equals 4.88, the pKb equals 9.18. And therefore, Kb equals 7.6 times 10 to the minus 10. Now we drop the following equilibrium table denoting quinoline by Q and its conjugate acid by QH+. So in this particular case, as initially prepared, quinoline will have a concentration of 0.010 moles per liter, and before there's any opportunity for equilibration to occur chemically, the initial concentrations of hydroxide and conjugate acid will be 0. We'll also see, because this is a 1-to-1-to-1 stoichiometric relationship in this acid-base equilibria, that we will see a minus X change in concentration for quinoline and positive X for both hydroxide and the conjugate base. Because of this, the equilibrium concentration can be expressed for quinoline as 0.010 minus X, and the equilibrium concentration of both hydroxide and the conjugate acid are each X. The value of X is found by inserting the equilibrium concentration into the expression for Kb. Kb equals concentration of hydroxide times the concentration of the conjugate acid divided by the original species, in this case quinoline. So it'll be X squared divided by 0.010 minus X. We can, in this example, assume that X is substantially less than 0.010, and therefore simply substitute 0.100 for the expression assuming X is is insignificant in determining that value. So in this case, we can rearrange, solve for X, and that will give us the value 2.8 times 10 to the minus 6th. This value is consistent with the assumption that X is substantially less than 0.010. Therefore, pOH equals the negative log of 2.8 times 10 to the negative 6th, because that's the concentration of hydroxide, and that's going to equal 5.55. Consequently, pH equals 14 minus 5.55 equals 8.45, or about 8.4. So the fraction protonated could be described as this, or about 1 molecule for every 3,500 molecules. If you'd like to try another one of these on your own, you can use this self-test where pKa for the first protonation of nicotine is 8.02, and you can ask yourself what's the pH of the fraction of molecules protonated in a 0.015 moles per liter aqueous solution of nicotine. Now, moving along to polyprotic acids. A polyprotic acid is a molecular compound that can donate more than one proton, meaning it has more than one acidic proton. Two examples are sulfuric acid, H2SO4, which can donate up to 2 protons, and phosphoric acid, H3PO4, which can donate up to 3. A polyprotic acid is best considered to be a molecular species that can give rise to a series of Bronsted acids as it donates its succession of protons. Therefore, sulfuric acid is the parent of 2 Bronsted acids, H2SO4 itself and HSO4-, and phosphoric acid is the parent of 3 Bronsted acids. For species H2A with 2 acidic protons, such as H2SO4, the successive equilibria we need to consider are as follows. The first, in which H2A dissociates its first proton, forming a hydronium, and the second, where the conjugate base of the first dissociation acts as an acid in a successive dissociation, where HA- dissociates, giving up its proton to react with water to form a second hydronium and forming a different conjugate base, A2-. Each of these can be described as different equilibria. And the first proton is always the most acidic, easiest to give up. As we start to add charge, giving up a positive charge becomes harder because of its natural attraction to the negative charge on the conjugate base. Therefore, each successive dissociation becomes less likely to occur. Therefore, each successive dissociation indicates a weaker acid. So, in the first of these equilibria, HA- is the conjugate base of H2A, and in the second, HA- acts as the acid, and A2- is the conjugate base. And the values for given in Table 8.2 for a variety of polyprotic acids. In all cases, like I mentioned earlier, Ka2 is smaller than Ka1, typically by 3 orders of magnitude for small molecular species, because the second proton is more difficult to remove, partly on account of the negative charge of the conjugate base. Enzymes are polyprotic acids, for they possess many protons that can be donated to a substrate molecule or to a surrounding aqueous medium of the cells. For them, successive acidity constants vary much less because the molecules are so large that the loss of a proton from one part of the molecule has little effect on the ease with which another, some distance away, may be lost. So they're a little bit more robust in terms of seeing these large differences in pKa's between successive losses of protons. So, an example. Calculating the concentration of carbonate ion in carbonic acid. So groundwater contains dissolved carbon dioxide, carbonic acid, hydrogen carbonate ions, and a very low concentration of carbonate ions. Estimate the molar concentration of CO32- ions in solution in which water and carbon dioxide gas are in equilibrium. So the strategy for this is we must be very cautious in the interpretation of calculations involving carbonic acid because equilibrium between dissolved CO2 and H2CO3 is achieved only very slowly. In organisms, attainment of equilibrium is facilitated by the enzyme carbonic anhydrase. We start with the equilibrium that produces the ion of interest, such as A2-, and write its activity in terms of the acidity constant for its formation, Ka2. That expression will contain the activity of the conjugate acid, HA-, which we can express in terms of the activity of its conjugate acid, H2A, by using the appropriate acidity constant. This equilibrium dominates all the rest, provided that the molecule is small, and therefore marked difference exists between acidity constants, so it may be possible to make an approximation at this stage. So, for our solution, we can see that CO32- ion, the conjugate base of the acid HCO3-, is produced in the following equilibrium. And that we can describe its equilibrium acidity constant, Ka2, as the following. Therefore, we can rearrange to find the concentration of CO32- simply by knowing the concentrations of HCO3-, the pH, and therefore the concentration of hydronium, and Ka2. The HCO3- ions are produced in the following equilibrium, where H2CO3 plus water is in equilibrium forming hydronium plus HCO3-. One hydronium ion is produced for each HCO3- ion produced. These two concentrations are not exactly the same because a little HCO3- is lost in the second deprotonation, and the amount of H3O plus hydronium has been increased by that quantity. Also, HCO3- is a weak base and abstracts a proton from water to generate H2CO3. However, those secondary changes can safely be ignored in an approximate calculation. Because the molar concentrations of HCO3- and hydronium are approximately the same, we can suppose that their activities are also approximately the same and set their concentrations or activities equal to each other. When this equality is substituted into the expression, and we make the approximation that the activity of CO32- equals the concentration, then we can obtain the following. Because we know from table 8.2 that pKa2 is 10.25, it follows the concentration of CO32- equals 5.6 times 10 to the minus 11 under standard conditions. And therefore, if equilibrium has in fact been achieved, that the molar concentration would be 5.6 times 10 to the minus 11 moles per decimeter cubed, and within approximations we've made independent of the concentration of H2CO3 present initially. And here's another example. Instead of walking all the way through this example, what I'm going to do is encourage everybody to read through it in detail, because trying to speak out loud all of the adjustments to the equations is actually quite cumbersome, both for the speaker and for the audience. But once you get through it, I'd like to take everyone's attention to this following paragraph, where we can summarize the behavior found in this example by 3 important points. So please read through the example, make sure you can rationalize it, and then go through those important summary points. Then moving along to amphiprotic systems, and then salts and water. An amphiprotic species is a molecular ion that can both accept and donate protons. For example, HCO3- can act as an acid to form CO32- and as a base to form H2CO3. The question we need to tackle is the pH of a solution of a salt with an amphiprotic anion, such as solution of NaHCO3. Is the solution acidic on account of the acidic character, or is it basic on account of the anion's basic character? As shown in the derivation, which is in the text, the pH of such a solution is given by the following. The pH equals -1/2 the pKa1 plus pKa2. This expression is valid provided the molar concentration of the salt is high in the sense used in the notation derived in A1, where F is the formal concentration of the salt. If these conditions are not satisfied, a much more complicated expression can be used, but we don't need to go through that. So the bottom line is, if you know the pK1 and 2, you just add them, divide by 2, and that'll give you the pH of the solution, which will tell you if the amphiprotic substance behaves as an acid or base, depending on the relative strengths of their two different acid character and their base character. Now, let's talk about salts in water. The ions present when a salt is added to water may themselves be either acids or bases and consequently affect the pH of the solution. For example, when ammonium chloride is added to water, it provides both an acid, ammonium, and a base, chloride. The solution consists of a weak acid, ammonium, and a very weak base, chloride. The net effect of the solution is acidic. Similarly, a solution of sodium acetate consists of a neutral ion, the sodium, and the base, the acetate. The net effect is the solution is basic and its pH is greater than 7. To estimate the pH of the solution, we proceed in exactly the same way as for the addition of a conventional acid or base. For in Bronsted-Lowry theory, there's no distinction between conventional acids like acetic acid and the conjugate acids of bases like ammonium. For example, to calculate the pH of 0.01 molar solution of ammonium chloride at 25 degrees Celsius, we proceed exactly as in example 8.1, taking the initial concentration of the acid, the ammonium, to be 0.010 moles per decimeter cubed, and then take the Ka to use its acidity constant of the acid, ammonium, which is listed in table 8.1. Alternatively, we can use Kb for the conjugate base, ammonia, of the acid, and convert that quantity to Ka by using the relationship of Ka times Kb equals Kw. Regardless, we find pH equals 5.63, which is on the acid side of neutral. Exactly the same procedure is used to find pH of a solution of a salt of a weak acid, such as sodium acetate. The equilibrium table is set up by treating the anion, in this case acetate, as a base, which it is, and using for Kb the value obtained from the value of Ka for its conjugate acid, in this case acetic acid. So, let's talk about acid-base titrations a little bit. Acidity constants play an important role in acid-base titrations, for it can use them to decide the value of the pH that signals the stoichiometric point, the stage at which the stoichiometrically equivalent amount of acid has been added to a given amount of base. The plot of the pH of the analyte, the solution being analyzed, against the volume of titrant, the solution in the burette, is called the pH curve. It shows a number of features that are still of interest even nowadays when many titrations are carried out in automatic titrators. Automatic titration equipment is built to make use of concepts we describe here. And although lots of titrations do take place automatically, titrating by hand is still not a lost art, and it still occurs in the laboratory routinely. So, first, consider the titration of a strong acid with a strong base, our simplest example, such as the titration of hydrochloric acid with aqueous sodium hydroxide, in where the reaction is aqueous hydrochloric acid plus sodium hydroxide react to form aqueous sodium chloride, which are just spectator ions, plus water. Typical neutralization reaction. Initially, the analyte, hydrochloric acid, has a low pH. The ions present at the stoichiometric point, the sodium ion from the strong base and the chloride ions from the strong acid, barely affect pH whatsoever. So the pH is that of almost pure water, meaning pH equals 7. After the stoichiometric point, when base is added to a neutral solution, the pH rises sharply to a high value. The pH curve for such titration is shown in figure 8.3. And that's what we're really seeing here, where we have no buffering effects. And as the acid is consumed, the hydrochloric acid is consumed initially, the pH is adjusting slowly, and then as it starts to be consumed completely, we get a rapid increase in pH until it reaches the equivalent point, or stoichiometric point as per this text, but you can also call it the equivalence point at pH 7, where we have neutrality, and then it continues to rise rapidly because as we continue to titrate in hydroxide, the pH is moving up faster and faster and faster. So, we've all seen this example in 100-level chemistry. Let's move on. So, figure 8.4 in the bottom corner of this slide shows the pH curve for the titration of a weak acid, such as acetic acid with a strong base, sodium hydroxide. At the stoichiometric point of the solution, at the stoichiometric point, the solution contains the conjugate base, which is acetate, and sodium ions together with any ions stemming from autoprotolysis, which is trivial in this particular case. The presence of Bronsted base acetate in the solution means that we can expect a pH greater than 7. Because unlike the presence of water from a strong acid, strong base titration, once we've reached the equivalence point now, we have consumed our weak acid and we've generated this conjugate base, which does act as a base. In a titration of a weak base, such as ammonia, and a strong acid hydrochloric, the solution would contain the conjugate acid, ammonium, and chloride ions at the stoichiometric point. Because chloride is a very, very weak Bronsted base, and ammonium is a weak Bronsted acid, the solution is acidic, and the pH would be less than 7. So now we consider the shape of the pH curve in figure 8.4 in terms of the acidity constants of the species involved. The approximations we make are based on the fact that the acid is weak, and therefore that HA is more abundant than any conjugate base A- ions in solution. Therefore, when weak acid HA is present, it provides so many hydronium ions, even though it's a weak acid, that they greatly outnumber any hydronium ions that come from the very feeble autoprotolysis of water. Therefore, we can ignore the effect of water in this relationship. Finally, when excess base is present, after the stoichiometric point has been passed, the hydroxide ions it provides dominate any that come from the water. To be specific, let's suppose that we're titrating 25 cubic centimeters of 0.10 molar acetic acid with 0.20 molar concentration solution of sodium hydroxide at 25 degrees Celsius. We can calculate the pH of at the start of the titration of a weak acid with a strong base, as explained in example 8.1, and find pH equals 2.9. The addition of titrant converts some of the acid to its conjugate base in the following reaction, where our weak acid, acetic acid plus hydroxide, will react to form some liquid water plus the conjugate base acetate. Suppose we add enough titrant to produce a concentration of base of the conjugate base and simultaneously reduce the concentration of the acid. Then, because the acid and its conjugate base remain at equilibrium, we can write the expression for Ka, where it's the concentration of the acid over the concentration of the hydronium times the concentration of our conjugate base over the concentration of our weak acid. So with this in place, we can rearrange and actually write the following expression for the Henderson-Hasselbalch equation, where pH equals the pKa minus the log of the concentration of our acid over the concentration of our base pair. So, here's another really nice example for estimating pH at an intermediate stage in a titration. And I'm going to let you guys pause the slide and work your way through this example. And moving on, now that we've worked through the example, halfway to the stoichiometric point, when enough base has been added to neutralize half the acid, the concentration of acid and base are equal. And because log of 1 equals 0, the Henderson-Hasselbalch equation gives the following: pH equals pKa. So under the conditions of the equivalence point, pH equals pKa. In the present titration, we see that at this stage of the titration, pH equals 4.75. Note that the pH curve in figure 8.4, how much more slowly the pH is changing compared with initially. This point will prove important shortly. Equation 814, pH equals pKa, implies that we can determine the pKa of the acid directly from the pH of the mixture. Indeed, an approximate value for the pKa may be calculated by recording the pH during a titration and then examining the record for the pH halfway to the stoichiometric point. At the stoichiometric point, enough base has been added to convert all of the acid to its base, so the solution consists nominally only of the acetate ions. These ions are Bronsted bases, so we can expect that the solution to be basic with a pH well above 7. We've already seen how to estimate the pH of a solution of a weak base in terms of its concentration B. So all that remains to be done is to calculate the concentration of acetate at the stoichiometric point. It's very important to note that the pH at the stoichiometric point of a weak acid strong base titration is on the basic side of neutrality. At the stoichiometric point, the solution consists of a weak base, the conjugate base of the weak acid, and neutral cations, sodium in this particular case. The general form of pH curve suggested by these estimates throughout a weak acid strong base titration is illustrated in figure 8.4, which is 2 slides previous. You want to go revisit it. The pH rises slowly from its initial value, passing through values given by Henderson-Hasselbalch equation when the acid and conjugate base are both present in equal concentrations. It then changes rapidly to and through the value characteristic of a solution of a salt, which takes into account the effect of the pH of the solution of a weak base, the conjugate base of the original acid. The pH then climbs less rapidly towards the value corresponding to a solution consisting of excess base, and finally approaches the pH of the original base solution when so much titrant has been added that the solution is virtually the same as the titrant itself. The stoichiometric point is detected by observing where the pH changes rapidly through the value calculated in the illustration at the beginning of the section. A similar sequence of changes occurs when the analyte's weak base, such as ammonia, and the titrant's a strong acid, such as hydrochloric acid. In this case, the pH curve is like that of shown in 8.5 in the bottom corner. The pH falls as the acid is added, plunges through the pH corresponding to a solution of weak acid, and then slowly approaches the pH of the original strong acid. The pH of the stoichiometric point is that of the solution of weak acid and is calculated as illustrated in example 8.2. So, now we're set up to talk about buffers. The slow variation of the pH when the concentrations of the conjugate acid and base are nearly equal, when pH is approximately equal to pKa, is the basis of buffer action. The ability of a solution to oppose change in pH when small amounts of strong acids and bases are added. In an acid buffer solution, one that stabilizes solution at pH below 7 is typically prepared by making a solution of a weak acid and a salt that supplies its conjugate base, in this case a combination of acetic acid and, say, sodium acetate. A basic buffer, one that stabilizes solution above pH of 7, is prepared by making a solution of a weak base, such as ammonia, and a salt that supplies its conjugate acid, such as ammonium chloride. Physiological buffers are responsible for maintaining pH of blood within a narrow range between 737 to 743, where stabilizing the active conformations of biological macromolecules and optimizing the rates of biochemical reactions are incredibly important. An acid buffer stabilizes the pH of a solution because the abundant supply of conjugate base ions from the salt can remove any hydronium ions brought in by additional acid. Furthermore, the abundant supply of weak acid molecules can provide hydronium ions to react with any base that is added. Similarly, in a base buffer, the weak base can accept protons when an acid is added, and its conjugate acid can supply protons if a base is added. Therefore, by limitations associated with its concentration in the buffer can consume acids or bases and convert them into weaker conjugates, buffering that adjustment to pH. These abilities can be expressed quantitatively by considering the changes in equilibrium composition of hydronium ions in the presence of a buffer. This behavior is best illustrated with an example. And here we have our example, which illustrates this particular change. Please pause the slide and read through the example to make sure it makes as much sense as possible, particularly with how we are looking at the Henderson-Hasselbalch equation. Now, one thing I do want to point out is that the Henderson-Hasselbalch equation is functionally pH equals pKa minus the log of concentration of our base over our acid. And for buffered solutions, what this really does for us is it tells us that pH fundamentally equals pKa if we have a 1-to-1 ratio of our base to our acid, if they're equimolar, because the log of 1 is 0, so we would have no adjustment. But what this function really does for us is provides an adjustment factor for how pH varies from pKa based on the ratio of our conjugate base to our acid. So Henderson-Hasselbalch is just an equivalence of pH to pKa with an adjustment factor based on the ratio of the components of the buffering system. So with that in mind, we'll go ahead and work through this example and with a little pause, and then we'll get back to buffering. So, quick segue, buffering action in blood. The pH of blood in a healthy human varies between 7.37 and 7.43. There are two buffer systems that help maintain pH of blood relatively constant. One arising from carbonic acid bicarbonate ion equilibrium, and another involving protonated and deprotonated forms of hemoglobin, the protein responsible for the transport of oxygen. So, carbonic acid forms in blood from the reaction between water and CO2 gas, which comes from inhaled air and is also a byproduct of metabolism. In red blood cells, this reaction is catalyzed by the enzyme carbonic anhydrase. Aqueous carbonic acid then deprotonates to form a bicarbonate ion, as shown here. The fact that pH of normal blood is approximately 7.4 implies that the ratio of the conjugate base to the acid is approximately 20. The body's control of pH of blood is an example of homeostasis, the ability of an organism to counteract environmental changes with physiological responses. For instance, the concentration of carbonic acid can be controlled by respiration. Exhaling air depletes the system of CO2 and therefore H2CO3, so that pH of the blood rises when air is exhaled. Conversely, inhalation increases the concentration of carbonic acid in blood and lowers its pH. The kidneys also play a role in the control of the concentration of hydronium ions. Therefore, ammonia formed by the release of nitrogen from some amino acids, such as glutamine, combines with excess hydronium ions, and the ammonium ion is excreted through urine. The condition known as alkalosis occurs when the pH of blood rises above 7.45. Respiratory alkalosis is caused by hyperventilation or excessive respiration. The simplest remedy for breathing consists of breathing into a paper bag in order to increase the levels of CO2. Metabolic alkalosis may result from illness, poisoning, repeated vomiting, or overuse of diuretics, or the consumption of aspirin. The body may compensate for the increase in pH of blood by decreasing the rate of respiration. Acidosis occurs when pH of blood falls below 7.35. In respiratory acidosis, impaired respiration increases the concentration of dissolved CO2 and lowers the blood's pH. The condition is common in victims of smoke inhalation and patients with asthma, pneumonia, and emphysema. The most efficient treatment consists of placing the patient in a ventilator. Metabolic acidosis is caused by the release of large amounts of lactic acid or other acid byproducts of metabolism, which react with hydrogen carbonate ions to form carbonic acid, thus lowering our blood's pH. The condition is common in patients with diabetes and severe burns. The concentration of hydronium ions in blood is also controlled by hemoglobin, which can exist in deprotonated and protonated forms, depending on the state of the protonation of several amino acid residues in the protein surface. The carbonic acid bicarbonate ion equilibrium and proton equilibrium in hemoglobin also regulate the oxygenation of blood. The key to this regulatory mechanism is the Bohr effect, the observation that hemoglobin binds O2 strongly when it's deprotonated and releases O2 when it is protonated. It follows that when dissolved CO2 levels are high and the pH of blood falls slightly, hemoglobin becomes protonated and releases bound oxygen to tissues. Conversely, when CO2 is exhaled and pH rises slightly, hemoglobin becomes deprotonated and binds oxygen. This can partially be thought of as an important response to the production of lactate in the blood during periods of anaerobic metabolism as an extra. Now, let's talk about indicators quickly. The rapid change of pH near the stoichiometric point of an acid-base titration is the basis of indicator detection. An acid-base indicator is a water-soluble organic molecule and conjugate base in which those two forms differ in color. The two forms are in equilibria in solution. The pK of the indicator of some indicators are listed in the next slide in Table 8.3, and this isn't something that you need to memorize, obviously, but you may actually need it to solve a few problems regarding indicators. The ratio of the concentration of the conjugate acid and base forms for the indicators will be as follows. And this expression can be arranged after taking common logarithms to the following, and then be rewritten to show the following, where the log of the ratio of the conjugate base to the acidic form of an indicator approximately equal to the pH minus the pK of the indicator. And this is just a manipulation of the Henderson-Hasselbalch equation. So it's just an example-specific adaptation of Henderson-Hasselbalch. We'll see that as the pH swings from higher than pK indicator to lower than pK indicator, as acid is added to the solution, the ratio of the basic form of the indicator to the acidic form of the indicator swings from well above 1 to well below 1. And we see this in figure 8.7. At the stoichiometric point, the pH changes sharply through several pH units so that the molar concentration of hydronium changes through several orders of magnitude. This indicator equilibrium changes the indicator equilibrium changes so as to accommodate the change of pH with the acidic form of the indicator, the dominant species on the acid side of the stoichiometric point. When hydronium ions are abundant, the basic form of the indicator, ion minus, dominate on the basic side, when the base can remove protons from the acidic form. The accompanying color change signals the stoichiometric point of the titration has been reached. So the color, in fact, changes over a range of pH, typically from plus or minus 1. The pH halfway through a color change is indicated by pH equals the pKa of an indicator, where the two forms are in equal abundance, which is what you would ascertain from Henderson-Hasselbalch. So even though we use them all the time in the lab, care must be taken to use an indicator that changes color at the pH appropriate to the type of titration that you're interested in. Specifically, we need to match the endpoint of the stoichiometric point and therefore select an indicator for which the pK indicator is close to the pH of the stoichiometric point of your titration. Therefore, in a weak acid strong base titration, the stoichiometric point lies greater than 7, and we should select an indicator that changes at that pH. And here, as promised, is a table of indicators you may need for solving some homework problems, but not something you should commit to memory. Now let's move slightly away from acid-base equilibria and discuss solubility equilibria, which will give us a segue into the solubility constant, as well as a few other factors. So just a few more slides to go in this chapter, 4 more slides to be specific. So a solid dissolves in a solvent until the solution and the solid solute are in equilibrium. At this stage, the solution is said to be saturated, and its molar concentration is the molar solubility of the solid. That the two phases, the solid, solute, and the solution, are in dynamic equilibrium implies that we can use equilibrium concepts to discuss the composition of the saturated solution. You should note that a solution or a solubility equilibrium is an example of a heterogeneous equilibrium in which the species are in different phases, the solid, solute, and the solution. The properties of an aqueous solution of electrolytes are commonly treated in terms of equilibrium constants, and in this section, we'll confine our attention to that. We shall also limit our attention to sparingly soluble compounds, which are compounds that dissolve only slightly in water. This restriction is applied because the common ion-to-ion interactions are a complicating feature of more concentrated solutions, and more advanced techniques are needed before we can calculate that reliably. Once again, we shall we'll concentrate on general trends and properties rather than expecting to obtain numerically precise results, and confine numeric calculations to systems at 298 Kelvin or 25 degrees Celsius. So, the solubility constant. The heterogeneous equilibrium between sparingly soluble ionic compounds such as calcium hydroxide and its ions in aqueous solution is as follows, where we have our calcium hydroxide in solid form, CaO2OH2, is in equilibrium with calcium and 2 equivalents of hydroxide. And we can show this relationship through the equilibrium of the concentration of the products over the concentration of the reactants. However, because the activity of the calcium hydroxide equals 1, meaning we don't take into account because it's a solid and is therefore unchanging in concentration, we can just focus on the concentration of our 2 products because they're in aqueous solutions. The equilibrium constant for an ionic equilibrium such as this, bearing in mind that the solid does not appear in the equilibrium expression, is called the solubility constant, which is also called the solubility product constant, or simply the solubility product. As usual, for very dilute solutions, we can replace the activity of a species, J, by the numeric value of its molar concentration. And that's what I recommend doing. Experimental values for solubility constants are given in table 8.4, which we'll see on the next slide. We can interpret the solubility constant in terms of the numeric value of molar solubility, S, of a sparingly soluble substance. For instance, it follows from the stoichiometry of the equilibrium equation written above that the molar concentration of calcium ions in solution is equal to that of calcium hydroxide dissolved in solution. So S would equal the concentration of calcium ions. Likewise, because the concentration of hydroxide is twice that of the calcium hydroxide formula units, it follows that S would equal 1/2 the concentration of hydroxide anions. Therefore, provided it's permissible to replace activities by molar concentrations, K sub S would approximately equal to 4S cubed, from which it would follow that S would equal 1/4 Ks cube root. This expression is only approximate because ion-ion interactions have been ignored. However, because the solid is sparingly soluble, the concentrations of ions are low, and the inaccuracy is moderately low. Therefore, table 8.4, where Ks equals 5.5 times 10 to the minus 6, so S would approximately be equal to 1 times 10 to the minus 2, and the molar solubility is 1 times 10 to the minus 2 moles per decimeter cubed. Solubility constants, which are determined by electrochemical measurements of the kind described in the following chapter, provide a more accurate way of measuring solubilities of very sparingly soluble compounds because of the direct measurement of the mass that dissolves. Because solubility products are equilibrium constants, they may be calculated from thermodynamic data, particularly the standard Gibbs energy of formation of ions in solution and the relation delta G equals negative RT ln K. The direct determination of solubilities is very difficult for almost insoluble salts. Another application is to the discussion of qualitative analysis, where judicious choice of concentrations guided by the value of K sub S, or the equilibrium of S, can result in the successive precipitation of compounds, for instance sulfides, and the recognition of the heavy elements like barium present in a mixture. So, finally, the common ion effect. The principle that an equilibrium constant remains unchanged, whereas the individual concentrations of species may change, is applicable to solubility constants and may be used to assess the effect of the addition of species to solutions. An example of particular importance is the effect of the solubility of a compound of the presence of another freely soluble solute that provides an ion in common with a sparingly soluble compound already present. For example, we may consider the effect of solubility of adding sodium chloride to a saturated solution of silver chloride, the common ion in this case being chloride. We know what to expect from Le Chatelier's principle. When the concentration of common ion is increased, we can expect the equilibrium to respond by tending to minimize that increase. As a result, the solubility of the original salt can be expected to decrease. To treat the effect quantitatively, we note that the molar solubility of silver chloride in pure water is related to the solubility constant S. It's approximately equal to K sub S, the square root of it. To assess the effect of the common ion, we suppose that chloride ions are added to concentration which greatly exceeds the concentration of the same ion that stems from the presence of silver chloride. Therefore, we can write the following. It's very dangerous to neglect deviations from ideal behaviors in ionic solutions. So from now on, the calculation will only be indicative of the kinds of changes that occur when a common ion is added to a solution of a sparingly soluble salt. The qualitative trends are reproduced, but the quantitative calculations are unreliable. With these remarks in mind, it follows that the solubility S' of silver chloride in the presence of added chloride is as follows. The solubility is greatly reduced by the presence of the common ion. For example, whereas solubility of silver chloride in water is 1.3 times 10 to the minus 5 moles per cubic decimeter, in the presence of 0.10 molar sodium chloride, it's only 2 times 10 to the minus 9th moles per cubic decimeter, which is nearly 10,000 times less. The reduction of the solubility of a sparingly soluble salt by the presence of common ion is called the common ion effect. Even a salt that has no ion in common with a sparingly soluble salt can affect the latter solubility. At low concentrations of the added salt, the solubility of the sparingly soluble salt is increased. The explanation lies in a phenomenon that will move to center stage in Chapter 9, where we'll see that in aqueous solution, cations tend to be found near anions, and anions tend to be found near cations. That is, each ion is in an environment called an ionic atmosphere or opposite charge. The charge imbalance is not great because the ions are ceaselessly churned around by thermal motion, but it's enough to lower the energy of the central ion slightly. When a soluble salt is added to the solution of a sparingly soluble salt, the abundant ions of the latter form ionic atmospheres around the ions of the sparingly soluble salts. As a result of the lowering of energy that results, the sparingly soluble salt has a greater tendency to go into solution. That is, the presence of the added salt raises the solubility of the sparingly soluble salt. To estimate the effect of an added salt, mx, on a sparingly soluble salt, AB, we can write the solubility constant for AB in terms of activities. It follows so what we'll see in Chapter 9 is that the logarithm of the productivity-activity coefficients is proportional to the square root of the concentration C of the added salt, with the log of gamma A gamma B equals negative 2A square root of C, where A is a constant that depends on the identity of the solvent and the temperature for water. And for water at 25 degrees Celsius, A would be 0.51. Note that A times the square root of concentration increases with increasing concentration of salt added. So the log S, and therefore S itself, also increases as we anticipate. The important thing within this, because we're transitioning to Chapter 9 here, is that we know categorically how the addition of another salt can impact the solubility of a sparingly soluble salt. And that is it for Chapter 8. Moving on, next week I'll be posting the next lecture, and I'll be talking to you about that shortly.